All right, folks, let's get started here in Chapter 1, Section 2.1. It's called Limits and Continuity. And the objectives we're going to focus on in Section 2.1 are Objective 1, estimate limits numerically and graphically. And Objective 2, we're going to estimate left-hand and right-hand limits. And that will lead us to Objective 3, which will allow us to define the limit concept. In example 4, we'll briefly examine some limit theorems. And in Objective 5, we'll work on determining limits algebraically. In Objective 6, we're going to analyze indeterminate form. We're going to see the majority of our limits actually start off in indeterminate form. So we'll analyze how to handle that. In Objective 7, we're going to analyze the limit of a difference quotient. So that's an old topic from college algebra. And then in Example 8, we're going to take a brief look at what continuity is. So here we go. Let's get started here with Objective 1. This thing we're going to talk about the limit. The limit concept is actually the backbone of calculus. And the limit, what it really does is it says, what are happening to the function values as x, the independent variable x, gets really, really close to a specific number. So to introduce that concept, we're going to start off by finding a limit numerically. And to do that, we're going to just evaluate a function for different values of x that get closer and closer and closer to a given value. So for example, let's consider the function f of x equals x squared minus 4 over 2x minus 4. And we're going to construct a table of values, for x's that are close to x equals 2. Please note, x equals 2 is not in the domain of the function. X equals 2 would make the denominator 0. And we know you cannot divide by 0. So what the question is, and the limit concept is, we know we can't put 2 into the function. We cannot put 2 in for x. But what is happening to the functional values, the f of x's, or the y's if you prefer, as x gets really, really close to 2? So we're going to make a table of values, and we're going to guess what we think the functional values are getting close, are approaching or getting close to when x is really, really close to 2. So now notice this notation, that x, arrow, 2. That arrow is shorthand for the word approaches, so that is actually read x approaches 2. You can think that means as x is really, 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 really close to 2. So once we look at a table of values, then we're going to look at a graph of f to graphically support the numerical work. So typically what happens with an example, and this is going to be true going forward, you should write the example down, because I typically will head off to the chalkboard to work out the example. So for this one, it's going to be just slightly different. I've already pre-made, the table of values. So notice the x values I've already put into this table, the 1, 1.9, 1.99, 1.999, etc. We're going to put those values of x into the function, and we're going to see what comes out. And then we'll look at a graph. So before I head off to the board, because I'm going to fill in this table, once I get to the chalkboard, I just kind of want to, show you how I'm going to use my calculator to do this. So, let me pull up my calculator. And so let's see, y equals, so I got to put the function into y equals. So it's an x squared minus 4 divided by 2x minus 4. And I don't remember about my calculator. I haven't used it in a couple of weeks here. I'm going to see if my calculator's broken or if it needs fit, because I'm going to make a table of values. So what I'm talking about is I'm going to activate table set. So that's second window. Okay, everything's fine. You want to make, this is independent. You want to make sure that it's on ask. So if on your calculator it's currently on auto, you'd come down here and you would go over to ask and you would hit enter. So that gives you complete freedom of what values of x, what numbers you're going to put in for the independent variable x. Leave dependent at auto because we want the calculator to automatically compute what f of x is. So I'm going to make a table by putting these values in for x. I'm not going to put 2 in for x because I know that's going to, it's not going to work. You can't have 0 in the denominator. So let me look at the table. So let's see, x is 1, and then x is 1.9, enter 1.99, 1.999, and then, I'll go ahead and do the 2.001, 2.01, 2.1, and 3. So these are the values of y that I'm going to put into the table when I get to my chalkboard. When x is 1, the functional value is 1.5, then 1.95. So, but when I get to the chalkboard, I'm going to kind of make a guess right now that it looks like when x is really close to 2, I mean 1.999 is pretty close to 2. Doesn't that y value look like it's close to 2? And when x is 2.001, I mean that's pretty close to 2. Isn't that y value also close to 2? I think so. So I have an idea of what I think. As the x's get closer and closer and closer to 2, it looks like the y values are getting closer to 2. But you know what? Let's take a quick look at the graph. So let me look at my viewing window here. Let's see. You know what? I'm gonna make a square viewing window. So that's number 5. So here's the graph of the function. And it looks like when x is close to 2, here's an x value of 2. Doesn't it look like that y value is close to 2? All right. So here's what I'm going to do. I'm going to head off to the chalkboard. I'm going to put this table up on the chalkboard. I'm going to fill in the numbers that we just saw on the calculator, and I'll also put the graph up there because there's some really, really important notation that I need to introduce at the chalkboard. So, make sure you have, this written down, this example, because I'm heading off to the chalkboard. All right, folks, on this first example, I went ahead and filled in the numbers that we just saw on the calculator. When I used my calculator to put these values of x into the function. So those numbers you've already seen on my calculator. But what I wanted to introduce some notation. Keep in mind, let me draw a real number line here. And, here's 2, 3, 1. These values of x are starting over here to the left side of 2. So what I'm really doing is I'm picking, 1.9, 1.99, 1.999. Those values of x are getting closer to 2 from the left side of 2. So I want to introduce notation for that. X, that arrow means is approaching or is getting close to 2. And now to communicate that we're approaching 2 from the left side of 2, I'm going to put a little negative sign. It looks like in an exponent position. Similarly, these values of x, notice they started to the right of 2. 3, 2.1, 2.01, 2.001. So those values of x are getting closer to 2, but they're coming from the right side of 2. So my notation for that, the shorthand notation, x is approaching 2. Now to communicate it's coming from the right side of 2, I'll put a little plus sign in what looks like the exponent position. So I wanted to introduce this notation. X approaches 2 from the left side of 2. X approaches 2 from the right side of 2. And it looks like as x gets closer to 2 from the left side of 2, it looks like the functional values are getting closer to 2. And as x approaches 2 from the right side of 2, it looks like those functional values are also getting closer to 2. And then graphically, here's what the graph of that function looks like. There's actually a hole in the graph at 2, 2. And that's what the graph looked like. Now I know on my calculator screen when I graphed it, it just looked like a line. But trust me, there is a hole in the graph at 2. We know 2 is not in the domain of the function. You can't put 2 in here for x because the denominator will be 0. And we can't divide by 0. So I wanted to come to the board to introduce this notation, which we're going to see in the next slide here. You know, when I go back to the slides, you're going to see it real quickly. And I also wanted to focus on the graph, that there would be a hole in the graph. So let's head back to the slides and formalize this left hand and right hand limit notation a little bit more. All right, folks, at the chalkboard I introduced the idea of the concept of a left side limit and the right side limit. And let me just kind of formalize it here. The limit can approach from the left side of the value or the right side of the value. That's what creates what we call a left hand limit and a right hand limit. I introduced this notation on the board. The limit, and I'm going to read it out, the limit as x approaches a from the left, that negative sign means from the left side of a, of f of x, well that means the limit as x approaches a from the left side of a. That's what we call the left-hand limit. Likewise, what I had on the board, the limit as x approaches a from the right side of a. Remember the plus sign means we're approaching a from the right side of a. That's called the right-hand limit. Now the left-hand limit and the right-hand limit, as we saw, are going to be, very important, very instrumental. It's going to be key in how we define the limit. But you know what? I thought we would do one more example of making a table of values. So for this function, let's construct a table of values, close to x equals 3. I think you would see that 3 is not in the domain of that function, that if you put 3 in for the x's, the denominator would be 0. Can't divide by 0. So we're going to make a table of values, and we're going to try to determine what the left-hand and right-hand limit of the function is as x gets close to 3. So, for this one, here's the table of values for you. For this one, going to do something a little different. Why don't you pause the video and you do this example, see what you think the left-hand limit and the right-hand limit is. Once you've worked through this example, restart the video, and I'll be at the chalkboard discussing it, and hopefully you'll have it correct. All right, folks, I asked you to pause the video and complete this table of values to try to determine the left-hand and right-hand limit of this function as x approaches 3. So I wrote down the notation, limit as x approaches 3 from the left of this function, and the limit as x approaches 3 from the right of that function. So, if you filled in the table of values, this is what I come up with. When you put 2 in for x, you get negative 2.5. When you put 2.9 in for x, and then I'm gonna round this, it's negative 2.07. That's rounded. I think it was like negative 2.069. There was a lot of digits. I'm just rounding here. When you put 2.99 in for x, again, this is rounded, negative 2.007. When 2.99 went in for x, rounded, you get negative 2.0007. You can't put 3 in for x because the denominator would be 0. 3.01 in for x, again rounded, I had a negative 1.999. When 3.1 is in for x, again rounded, I had a negative 1.993. When 3.1 went in for x, again rounded, I had a negative 1.93. And when 4 went in for x, well, it was negative 1.125. So let's take a look here. The limit as x approaches 3 from the left side of 3 of the function 2x cubed minus 15x squared plus a 22x plus 15 all over x squared plus x minus 12. Well, as the x values are getting really close to 3 from the left side of 3, it looks like those y values, it looks like they're getting really close to negative 2. So I'm going to say the left side limit is negative 2. The limit as x approaches 3 from the right side of 3 of the function 2x cubed minus 15x squared plus a 22x plus 15 all over x squared plus x minus 12. Well, as the x values get closer and closer to 3 from the right side of 3, these x values are getting closer to 3 from the right side of 3. It looks like those y values are getting closer and closer to negative 2. So the left side limit is negative 2. The right side limit is negative 2. What we are going to see when we head back to the slides is because the left side limit and the right side limit are exactly the same, that's going to allow us to say the limit as x approaches 3 of 2x cubed minus 15x squared plus a 22x plus 15 over x squared plus x minus 12. It will allow us to say that the limit is negative 2. And that's because the left side limit and the right side limit, they were approaching the exact same number. So let's head back to the slides. And hopefully you were able to do this and you had the same conclusion as me. Let's head back to the slides and formalize this. All right, so hopefully you ended up seeing that the limit as x approaches 3 from the left side of 3 was a negative 2, and that the limit as x approaches 3 from the right side of 3 was also negative 2. And then I introduced that because the left-hand limit and the right-hand limit were the same, we could then say that the limit as x approaches 3 of the function is negative 2. And that's going to lead us into our official definition of a limit. So, for any function f, limit as x approaches a of f of x equals L, that means that as x approaches a, f of x approaches L. In other words, when x is really, really close to a from both sides of a, the functional values are really, really close to L. So another way to look at it is if the limit as x approaches a from the left side is L, and the limit as x approaches a from the right side is L, then the limit as x approaches a of f of x equals L. So if your left-hand limit and right-hand limit, if they happen to be two different numbers, then the limit does not exist. Well, look, if the left-hand limit does not equal the right-hand limit, then the limit does not exist. That's really important. One more important little tidbit. The limit as x approaches a, it doesn't depend on whether or not f of a exists or what f of a is equal to. As we've seen in our first two examples, we determined a limit, but the function wasn't even defined at that value of x. The value of x that we were approaching was a value of x that made the denominator 0. So what's really happening there, it doesn't matter. So, kind of moving on here, here are some limit theorems. So these limit theorems can help us in the algebraic evaluation of limits because, hey, folks, the numerical approach and graphical approach, they were nice to help us introduce the concept of a limit, but they are very inefficient, very time-consuming. So we need to have a better way to do this, a more algebraic way to find limits. So these limit theorems can help. So in these limit theorems that you're about to see, a, b, and n, they represent real numbers. And there are 7 of them. So the first one, kind of an important one, believe it or not. It says the limit as x approaches a if c is equal to c. Okay, c can be any number you can think of. So in English, it's the English for number 1 that's kind of important. The limit of a constant is that constant. It doesn't matter what x is approaching if it's just, finding the limit of a constant. The limit of a constant is that constant. So, you can read through the rest of these limit theorems, if you would like. What we are going to find, and, this is going to take us quickly to objective 5. What we are going to find, and this is just, my comment to you, instead of memorizing those limit theorems, let's start off by trying what is called the substitution principle. The substitution principle is very nice and friendly. The substitution principle says, first try direct substitution when attempting to do a limit algebraically. So first try direct substitution. So when you're trying to find the limit as x approaches a of f of x, first just try to compute f of a. That's the substitution principle. If you can compute f of a, if it works, you have found the limit. So, let's practice this. Let's determine the following limits. Got 3 parts here. Part A, we're going to find the limit as x approaches 10 of 8. In part B, the limit as x approaches negative 2 of x squared plus 4x plus 8. Then in part C, the limit as x approaches 6 of the cube root of 3x plus 8. So, folks, write this example down. Put them in your notes. Put this example in your notes because I'm heading off to the chalkboard to work through this example. All right, in this example, we were asked to determine the limits. The limit as x approaches 10 of 8. The limit as x approaches negative 2 of x squared plus 4x plus 8. And in part C, the limit as x approaches 6, the cube root of 3x plus 8. So we saw like 7 limit theorems, and I said, hey, rather than memorize those limit theorems, do the substitution principle. Try to do that first. However, in part A, it's the one that I highlighted, the one limit theorem I highlighted. The limit of a constant is that constant. 8 is a constant. So the limit as x approaches 10 of 8, the constant 8, the limit of a constant is that constant. It doesn't matter what x is approaching here. No matter what x is approaching, this limit would be 8. Probably the easiest limits to find. You probably hope to see a bunch of these on test 1. I mean, you won't, but it would be nice. Okay, part B. This is where we get to what I call the substitution principle. Try substitution. See if it works. Make that your first thing to do when asked to find a limit. Just try substitution. So here if we substitute, we get a negative 2 squared plus 4 times negative 2 plus 8. So that's 4 plus a negative 8 plus 8 gives us a 4. It worked. This limit is 4. Part C. Again, you're asked to find a limit. Try substitution. So we substitute. Get the cube root of 3 times 6 plus 8. That's the cube root of 18 plus 8, which is the cube root of 26. It worked. Substitution principle. It's kind of friendly. So here's what I'd like you to do right now. In section 2.1 in the exercises, I would like you to try number 27 and 39. So I'd like you to try those two. So here's what you do. Pause the video. Do those two. Once you've done those two, restart the video. I'll be here at the chalkboard working through them, and hopefully you got them correct. All right, hopefully you did 27 and 39 like I asked, and let's see if you got them correct. Hopefully you did. So in 27, you're asked to find the limit as x approaches negative 2 of 3x plus 1. So what is it we try first? That's right, the substitution principle. So we substitute. So we get 3 times negative 2 plus 1. That's negative 6 plus 1. Negative 5. That limit is negative 5. Substitution worked. In number 39, you are asked to find the limit as x approaches 0, the square root of 2x plus 3. Try substitution. See if it works. So we substitute 0 for the x. And see, 2 times 0 is 0. We get the limit to be square root 3. So it worked. Substitution worked. I mean, you may have noticed that I've said a couple of times now, try substitution, see if it works. That's because sometimes substitution is not going to work. Sometimes when you substitute, you get what is called an indeterminate form. So let's head back to the slides and talk a little bit more about indeterminate form. All right, that example, that was a pretty friendly example. Gave you a couple to try real quick. Hopefully you got those. See, finding limits, not that bad. However, sometimes the substitution, the direct substitution that we try first doesn't work. Sometimes when you try direct substitution, it produces an indeterminate form. Indeterminate form is when you substitute and you get 0 over 0. We don't know what 0 over 0 is. That's why it's called indeterminate form. In fact, if you look at the very first example that we did, if you do that substitution for that very first example we did, of this slideshow, it would be 0 over 0. So here's what we do. If you try substitution and you get the indeterminate form 0 over 0, you have to do another technique to determine the limit. Sometimes I just call this algebra magic. You need to do some algebra magic in order to help find the limit. And the vast majority of the time, in fact, almost all of the time for our purposes, this algebra magic is going to be factoring. So let's look at an example. Determine the following limits. Part A, the limit as x approaches negative 1 of x plus 1 over x squared minus 1. And then part B, the limit as x approaches negative 2 of x squared plus 5x plus 6 all over x plus 2. So go ahead, write this down. Got to get you into the habit of doing this. Write the example down, both parts, the directions, because I'm going to head off to the chalkboard and work through this example.
All right, in this example, we were asked to determine some limits. In part B, the limit as x approaches -1 of x plus 1 over x squared minus 1. First thing we try is substitution. Always try substitution first. So we try substitution, and substitution gives us, well, let's see, -1 comes in for x, -1 plus 1 is 0. -1 comes into the denominator, comes in here for x. -1 squared is 1. 1 minus 1 is 0. Substitution produced the indeterminate form 0 over 0. So substitution did not initially work. No biggie. We just need to do some algebra magic. And here's what most of the algebra magic is going to be. Most of the time, our algebra magic is going to be factoring. So if you look at the denominator, x squared minus 1, that's a difference of 2 squares. Hopefully you remember a difference of 2 squares, how it factors. This one factors to x plus 1 times x minus 1. And as soon as we factor, we see there's some stuff we can cancel. We can cancel the x plus 1s. So that leaves us with the limit as x approaches -1. Well, we'd still be left with a 1 in the numerator over x minus 1. Now try substitution and see if it works. So now we try substitution, and we get 1 over -1 minus 1. Well, -1 minus 1 is -2, so we have 1 over -2, or -1/2. That's the limit. So, to recap, you always try substitution first. We tried substitution, we got the indeterminate form 0 over 0. We had to do a little algebra magic, and then substitute, we got the limit. So part B, we're asked to find the limit as x approaches -2 of x squared plus 5x plus 6 all over x plus 2. So the first thing we try is substitution. So substitution gives us, well, let's see, -2 comes in for the x, so that's 4 plus -10 plus 6, 0, and the denominator is 0. So substitution gives us the indeterminate form 0 over 0. So that means we need some algebra magic. So algebra magic, we will, well, that's it. Most of the time we're going to factor. That's our algebra magic. So let's see, that numerator. Let's try to factor that numerator. So I'd have an x here and x here. Both signs are addition, so both signs here would be addition. I think of the factors of 6, and I come up with 2 and 3. We can now cancel out the x plus 2's. We're left then with the limit as x approaches -2 of x plus 3. It'd be x plus 3 over 1. I don't have to write that over 1. Now we can substitute. So now we substitute, and we get the limit is 1. So you're going to see this about 80% of the time, I would say, roughly. You try substitution, you get the indeterminate form, 0 over 0, so then you need to do some algebra magic. So to practice this, to make sure you're understanding the process, I have a couple of problems I'd like you to try right now. I'd like you to try in the section 2.1 exercises, numbers 42 and 43. So just like before, pause the video, do numbers 42 and 43. Once you've done them, restart the video, and I'll be here at the board working through them, and hopefully you have them correct. Alright, hopefully you did as I asked and you paused the video and you tried 42 and 43. Let's see if you got them correct. So in 42, you're asked to find the limit as x approaches 5 of x minus 5 over x squared minus 25. The first thing you should try is substitution. And substitution gives us the indeterminate form 0 over 0. which is a signal you need some algebra magic. So our algebra magic, we're going to factor the denominator. It's a difference of two squares. So it factors to x plus 5 times x minus 5. And then once we factored it, we can cancel out the x minus 5s. Keep in mind that leaves us with a 1 in the numerator. And now we try substitution. So we put the 5 in for the x. We get the limit to be 1/10. So hopefully you got that as well. You got 1/10 as the limit. 43 was the limit as x approaches 1 of x squared minus 1 over x plus 1. Well, when we do x squared minus 1 over x plus 1, and we try substitution, notice substitution gives us, well, that's 1 minus 1, 0 over 2. That's not indeterminate. 0 over 2 is 0. Or kind of looks like a donut. So, not all of them will be indeterminate form. The majority will be indeterminate form. But that one's just to keep us honest. So, let's head back to the slides and see what's next.
All right, folks, hopefully you saw that it's not too bad when you have indeterminate form, you know how to attack it. So before we go any further, a brief recap. When you're asked to find a limit, the first thing you should do is try direct substitution. It might work. Most of the time you try direct substitution, you're going to get 0 over 0. So when you get 0 over 0, you just need to do some algebra magic, and then hopefully direct substitution will work after you do some algebra magic and you can determine the limit. So hopefully you know that example made sense, and the couple of problems I asked you to do, you were getting dialed in on it. You know, the next objective we're going to look at is the limit of a difference quotient. And to build up to this, we're going to encounter some situations where it looks like there are two or more variables present, but some of them are actually treated as a constant. So for example, in this statement, the limit as h approaches 0 of 4x minus 9h. Now notice since this limit statement says limit as h approaches 0. So when it says limit as h approaches 0, we treat that x as a constant. You know, h is the only variable mentioned. So let's practice this. So here's an example. Determine the following limits. In part A, we're going to find the limit as h approaches 0 of 4x minus 9h. Part B, we'll find the limit as h approaches 0 of 2xh plus h squared over h. Then in part C, for the function f of x equals 3x squared minus 1, we're going to compute the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. That's kind of like that difference quotient that we're building up to. So again, folks, if you have to pause the video to write the example down, please pause the video. Because I'm going to head off to the chalkboard now and work through all three parts of this example.
All right, in this example, we're asked to find the limits, and in part A, it was the limit as h approaches 0 of 4x minus 9h. This is the limit as h approaches 0. X can be treated as a constant. It's just as h is getting closer to 0. So we do the same thing that we have been stressing here for a while. You try substitution. You're substituting 0 for the h. That's it. So you substitute 0 for the h. You get 4x minus 9 times 0. That limit is 4x. In part B, it's the limit as h approaches 0 of 2xh plus h squared all over h. So we're substituting 0 for the h. And I'm not going to write it down. I am going to say this, that if I do substitute 0 for the h, I'm going to get the indeterminate form 0 over 0, which means I need some algebra magic. So the algebra magic here would be to factor an h out of the numerator. And then once I factor out the h, I can then cancel it out. So we have the limit as h approaches 0 of 2x plus h. Now I substitute. I substitute 0 for the h. So I get 2x plus 0. So that limit is 2h. Now in part C, you were given the function f of x equals 3x squared minus 1. And you're asked to find the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. This is like that difference quotient that I was just talking about. So I'm just going to break this down into some pieces. I need to compute the f of 1 plus h. So remember, to evaluate a function, it doesn't matter what you're evaluating the function at, you're going to put 1 plus h in for the x. So that gives us a 3. Now we have to take 1 plus h and squared, so that's a 1 plus a 2h plus an h squared. And then I distribute the 3. And then I combine these like terms. So I get 3h squared plus 6h plus 2. That's the f of 1 plus h. The f of 1, because I have to know what the f of 1 is, I put 1 in for the x. And that gives me 2. So f of 1 is 2. So the limit as h approaches 0, f of 1 plus h minus f of 1 all over h, well, that's the limit as h approaches 0. So let's see, the f of 1 plus h, f of 1 plus h is right here, 3h squared plus 6h plus 2, minus f of 1. F of 1 is 2. And then if I combine like terms in the numerator there, the 2's cancel out. So I have the limit as h approaches 0 of 3h squared plus 6h over h. That's indeterminate form. If I substitute 0 for the h's, I get 0 over 0. So I'm going to have to do a little algebra magic, factor out an h. So I factor an h out of the numerator, cancel it with the h in the denominator, and I have the limit as h approaches 0, 3h plus 6, substitute in, and I had just enough room to get it on the board. That limit is 6. So, to make sure you understand how to do these problems, I have a couple of them I'd like you to do. So in the section 2.1 exercises, I want you to pause the video, and I want you to try number 57 and 66. And just like before, after you do 57 and 66, restart the video, and I'll be here at the board working through them. Alright, hopefully you paused the video and did 57 and 66. Let's make sure you have them correct. Hopefully you do. In 57 was the limit as h approaches 0 of 3xh plus h squared all over h. Try substitution. That's going to give you 0 over 0, which means you need some algebra magic. And here the algebra magic is factoring. In the numerator, we factor out an h. Once we factor out the h, we can cancel it out with the h in the denominator. And that leaves us with the limit as h approaches 0 of 3x plus h. Substitute 0 for the h, and we get the limit to be 3x. Okay, 66, there were two parts. You were given the function x squared plus 2. Part A, you were asked to find the f of 1 plus h. Part B, the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. So here we go, f of 1 plus h. So f of 1 plus h, we take 1 plus h, toss it into the function for x, and let's see, if we FOIL that out, 1 plus h quantity squared is a 1 plus a 2h plus h squared. Then combine the like terms. 1 and 2 is 3. So we have h squared plus 2h plus 3. So that's what the f of 1 plus h is. So in part B, well, to do this limit, well, check it out. We know what the f of 1 plus h is. It's h squared plus 2h plus 3. So let's take h squared plus 2h plus 3, put it in here for f of 1 plus h. Okay, now we have to compute the f of 1. So the f of 1 comes in for the x. Let's see, 1 squared is 1. 1 plus 2 is 3, so the f of 1 is 3. Combine like terms, just have a 3 minus 3, which is 0. And, well, if you try substitution here, you're going to see you have the indeterminate form 0 over 0, so you need some algebra magic. Factor in h out of the numerator. And once you factor it out, you can cancel it out. And that leaves you with the limit as h approaches 0 of h plus 2. Substitute 0 for the h, and you get the limit to be 2. So hopefully you got both of those. Now let's head on back to the slides.
All right, continuing on here in section 2.1, our final topic is going to be continuity. In algebra, you may have heard that a function is said to be continuous if its graph has no breaks in it, such as holes, gaps, jumps, vertical asymptotes. When you do have a hole in the graph of a function, or a gap, or a jump, or a vertical asymptote at x equals a, we say the graph is discontinuous at x equals a. It's not continuous there, which is said to be discontinuous. So here's the real deal, folks. On how we determine if a function is continuous at x equals a. So we say that a function f is continuous at x equals a if all of the following are true. So all three of the following things have to be true. Thing 1, f of a has to be defined. Thing 2, the limit as x approaches a of f of x, well, it has to exist. And then thing 3 is, the 1 and 2 have to be equal. Or mathematically, the way to write that is, the limit as x approaches a of f of x, that's the result of number 2, if it exists, must equal f of a. That's the result of number 1, if f of a is defined. So if something is not continuous at x equals a, it has to violate one of these 3 conditions. So let's look at an example. Let's determine the continuity of the function x squared minus 4 over 2x minus 4 at x equals 0 and at x equals 2. So again, write this in your notes. Pause the video if you have to, because I'm heading off to the chalkboard to analyze the continuity at these 2 different values of x.
All right, continuity is what we're looking at right now. And we're asked in this example to determine the continuity of f of x equals x squared minus 4 over 2x minus 4 at x equals 0 and at x equals 2. Now remember, to be continuous at a value of x, here to be continuous at x equals 0, three things must be true. So let's go through those three things one at a time. So thing one, f of 0, it has to be defined. So let's see if f of 0 is defined for this function. So we put 0 in for the x's, and we get 0 minus 4 over 0 minus 4, which is negative 4 over negative 4, 1. So f of 0 is defined. Thing 2, does the limit as x approaches 0 of the function, does the limit exist? Well, let's try to find the limit and see if it exists. Remember, the first thing you do in trying to find a limit is substitution. So you substitute, you get 0 minus 4 over 0 minus 4, which is negative 4 over negative 4, which is 1. Thing 3, does f of 0 equal the limit as x approaches 0? Well, here was the f of 0, 1. Here was the limit, 1. Does 1 equal 1? Sure does. So this function, we would say yes, it is continuous at x equals 0. All right, let's check it out at x equals 2. So is the function continuous at x equals 2? So we go through our three items on our checklist. So thing 1, is f of 2 defined? Well, f of 2 gives us a 2 squared minus 4 over 2 times 2 minus 4. Let's see, 2 squared is 4, 4 minus 4 is 0. 2 times 2 is 4, 4 minus 4 is 0. It's indeterminate. So is the function defined at x equals 2? Is f of 2 defined? No, it's not. It's indeterminate. So is f of 2 defined? F of 2 is not defined. So we don't have to go any further. Remember, in order to be continuous at a value of x, all three things must be true. This one is not true. F of 2 is not defined. So this function is not continuous at x equals 2. And, that's it for this example. So let's head back to the slides and let's quickly wrap up this, final little tidbit discussion on continuity.
All right, so hopefully we're, dialed into the continuity. Keep in mind, this is a calculus class now, not a college algebra class. If I ask you, on a lab quiz or a test, if a function is continuous at a specific value of x, and if you tell me it is not continuous, you have to tell me exactly why. Either it's because the function value is not defined, or the limit doesn't exist, or the limit doesn't equal the function value. It will not be acceptable to say, there's a hole in the graph, where there's a vertical asymptote. Those are college algebra appropriate answers. So a few more topics here about continuity. We can say a function is continuous on an open interval BC if the function is continuous for all values of x in the interval. Kind of file this away. A polynomial function, polynomials are very friendly functions. A polynomial function is continuous for all reals x. So for everything, a polynomial is continuous. A rational function, a polynomial over a polynomial, that's a rational function. A rational function is continuous for all real x, except for those values of x that makes the denominator 0, because we know you can't divide by 0. And then a radical function, or you could call it a rational exponent function, it's continuous for all real x as long as you're in the domain. So to practice this whole idea of finding intervals where functions are continuous, let's look at this example. Determine the intervals where the following functions are continuous. So just two of them. F of x is 4x cubed minus 2x squared plus 1.3x minus 5. And then in part B, f of x equals 3x minus 7 over 2x plus 1. So again, write these down because I'm going to head off to the chalkboard and work through them.
All right, folks, in this example, we were asked to determine intervals where the function is continuous. So in part A, we were given the function f of x equals 4x cubed minus 2x squared plus 1.3x minus 5. The first thing I notice is that's a polynomial function. It's a polynomial function. It has a degree of 3. That's just bonus information. But it's polynomial. Polynomial functions are continuous everywhere. So because it's a polynomial function, I would say it is continuous everywhere, from negative infinity to infinity, parentheses around both. Part B, you were given the function f of x equals 3x minus 7 over 2x plus 1. Note this is a rational function because you have a polynomial over a polynomial. So when you have a rational function, anytime you have a rational function, you're continuous at all values of x as long as that value of x does not make the denominator 0. So look at the denominator. What value of x makes the denominator 0? What value of x makes the denominator 2x plus 1 equals 0? Well, that value of x is negative 1/2. So this function is continuous for all values of x except negative 1/2. So writing that in interval notation, I would say it's continuous on negative infinity to negative 1/2, parentheses around both, parenthesis, union with parenthesis, negative 1/2 to infinity. So you know what, I'm going to ask you to do one of these, one real quick. So pause the video, go to the section 2.1 exercises, try number 86. So pause the video, do 86. Once you finish 86, restart the video. I'll be here at the chalkboard working through it. All right, at number 86, hopefully you paused the video, you tried it. You were asked to determine where the function 3x minus 7 over 2x plus 1 is continuous. So again, we have a rational function, and with this rational function, it's for what values of x would the denominator be 0? And hopefully you saw that value of x, that the denominator 0 is negative 1/2, because we just did that one. So actually number 86 was the last example we did, part B. So hopefully you got what we did in that example, that it was continuous. Oops. On negative infinity to negative 1/2, parenthesis, union with negative 1/2 to infinity. So when I did that example part B, I didn't even realize it was number 86. But that concludes section 2.1. So you are now able to do all the exercises that I have assigned for you to do and practice these concepts in section 2.1. Thanks for watching.